his work, his efforts at NOS. So Saeed, go ahead and you can get started from here.
Oh, okay. So I am Saeed Moghimi, and thanks Sikshia and others for giving this opportunity. I just will turn off my camera during the call just to reduce the bandwidth, and then for the Q&A, I guess we can turn on back again and have a lively Q&A. I have quite a bit of material to share today. I would try to finish by 45-minute mark, so hopefully at least to leave 10 minutes for question and answer. So first of all, just to make sure, do you see my screen?
Yes.
Okay. So today I want to talk about NOAA National Ocean Services, storm surge modeling, research, development, and operational services. And I am representing National Ocean Services storm surge modeling team today. As you can see here, have multiple people working together, and of course it takes a village to raise a child. So and we are not alone. And I intentionally marked the partner by red because we think that the partners are different from collaborators, and partners are the ones that kind of have a skin in the game. So, and these are really the partner that we have, very straightforward and very efficient kind of like a contribution, and they are also are worried as much as we are for the end product and reaching to the end goal. So we have academic partners, and of course our NOAA partners from National Ocean Services, from National Weather Services, and Oceanic and Atmospheric Research, and there are more serious collaborators, but I mentioned here mainly our important partners and like the very active partners. International, we have also international partners and industrial partners, and I hope I didn't miss anybody. And whenever I look at this list, I remember new people, so I have to add. And who am I? Just a very brief overview about who am I. I kind of have my PhD in civil engineering and hydraulics, and did a fellowship in physical oceanography. And since 2017, I am working at National Ocean Services as a UCAR scientist. And these are my background. Don't want to spend time on them more. And so the next question is what we do at storm surge modeling team at National Ocean Services. So we are developing a global and basin scale coastal ocean models. We are used to develop and work on two-dimensional horizontal model, but we also, in the past couple of years, we also start looking into three-dimensional coastal ocean models. And our main idea is to resolve high resolution situation in coastal area and impacted area by storm surge. So the main kind of idea is to support disaster mitigation, coastal resilience, and of course safe navigation. Being from Office of Coast Survey, we are also mandated to support a safety of navigation going in and out of a port for commercial navigation specifically. So who are our end users? So the main end user, as I mentioned kind of previously, for disaster mitigation, we are supporting storm surge forecaster at National Weather Services weather forecast offices to generate flood forecasts during storms. And of course, we are collaborating also with NOAA Ocean Prediction Center and other part of National Weather Services. And just put one example of one of those coastal flood statements here. At the same time, as I mentioned, being from Office of Coast Survey, we also work with mariners for piloting ships to navigate into ports safely and efficiently based on tide and current forecast. We are supporting multiple S111 and S100 kind of water surface elevation specifically, as well as we are also working on supporting for the current, surface current, for supporting commercial navigation. So just to summarize basically how we do what we do. So storm surge modeling team within coastal marine modeling branch and in CSTL, we are basically taking all the way from planning, research and development, operation and maintenance of the storm surge modeling infrastructure. It includes, see if I can get my laser pointer somehow activated. I cannot. I don't know why, but anyway. So research and development, research to operation, operational implementation and support, as well as regular upgrade and maintenance, and its dissemination. As you can see here in this flow chart, starting from research and development to RTO and implementation. And basically then we are working also on how to disseminate the result, providing guidance, hindcast, also planning to support more efficiently the S100 and S400 and risk maps to end users. And of course, we will receive feedback from the community and end user and try to generate or kind of implement regular updates and upgrades to our modeling portfolio. Our vision for next generation storm surge model at National Ocean Services, we are thinking to extend our coverage to global and basin scale coverage, to have adaptive and flexible high resolution models. So we want to go from 2 kilometer all the way to 25 meter resolution, to make sure we are resolving all the features and hydraulic connectivity in coastal areas. Always looking into advanced numerical methods and latest technology to ensure optimal performance. We are thinking in basically to have a seamless, to have the capability to seamlessly switch between 2D and 3D models based on the end user needs. For instance, if we want to support navigation, we need to provide surface current. Therefore, we need to have a 3D model. However, if we want to do purely storm surge modeling and perhaps we want to do ensemble, you should be able to switch to 2D in order to reduce the computational needs, so we can use the same computational resources for multiple ensemble. I don't know why this pointer goes crazy. Anyway, we are also looking to different architecture. We want to develop the models that can be run both on conventional HPC platform as well as on cloud environment. And also we want to resolve relevant physics, basically to couple storm surge models to waves, inland hydrology, sea ice, and other relevant physics in the area. One thing that came out is that as we are pushing for high resolution, efficient input-output could be a bottleneck, and that's also something we are thinking about. And maybe most importantly, we want to always make sure that the model we are developing has active community support. Excuse me. So current product and services. At the moment, we have global surge and tide operational forecast system in operation. So this is basically our global model. We had a recent upgrade in just a couple of days, less than a month ago, more or less. And I'm going to talk about it a little bit in more detail. We also have a pre-operational system that right now we are working on. That's inland coastal flooding guidance system. And in parallel to that, in a research and development part, we are also working on a variety of different systems and products. One of them is Coastal Act. So we are supporting Coastal Act program by providing the storm surge model component. We are also working on upgrading and updating Hurricane Surge on Demand HSOFS system. So this system is not in operation at the moment. However, we have received some funds from Hurricane Supplemental and other sources of funding. So we are working on upgrading it, and hopefully we will have a conversation with National Hurricane Center in terms of what would be the plan for future operation of this system down the line. We are also working on enhancing Northern Pacific and, in general, Pacific modeling capabilities, both in support of disaster prevention and safe navigation. So this is a kind of just to give you an idea about the variety of projects that right now is being handled, and not directly by us. Most of these projects are in terms of collaboration or partnership with academia, and we are partnering with them. And some of these projects are directly handled and implemented by the team at National Ocean Services. Just to give you some type of an idea about the projects that we are and the kind of the variety of the projects that we are working on. Going to the next slide. So from here, I would just try to go more or less topic by topic and talk about some of the major work that we are doing and achievement, and kind of review them for you today. So one of the activities that we are very much involved with is coastal ocean modeling, model coupling development. We are following a unified forecast system. So the funding for this specific activity comes from really different projects like Coastal Act or NOAA Water Initiative. However, we try to do the implementation always have in mind best practices from unified forecast system. So this is basically the coupling paradigm that we are following. Being from, again, National Ocean Services and looking at coastal ocean model at the center, we want to make sure we have a good kind of coupling to wave model, inlet hydrology model, and of course, normally being forced these models by numerical weather model or even providing feedback. So having this coupling paradigm in mind, we also want to make sure we are providing enough products and updates and to support navigation support, disaster mitigation, and other type of downstream modeling products, and of course supporting the end users. So just to show you the coastal coupling application code base that right now we are developing. This code base is currently hosted under NOAA OCS modeling webpage, and we are, as you can see here, multiple models is already kind of have their cap, and these are all developed based on NUOPC under NEM's a driver, and so we have multiple models already implemented and being tested in the coastal coupling application that we are developing, of course in collaboration with multiple people from EMC and other parts of NOAA and even international collaborators. This is, again, just to give you a little bit more detailed information about what are the components right now we are working on. So in terms of coastal ocean components, right now, ATSIC model CAP in NOPC is actually developed a couple of years ago, and it's completely validated, a couple of papers on it. SCISM and FVCOM models are in the process of validating, and the CAP is implemented, however, is not yet validated. So we are working closely with the developers of and community of all these coastal ocean models to make sure they are getting the implementation necessary. In terms of atmospheric forcing, we internally are basically implementing PAM model. It stands for Parametric Hurricane Model. It's a Fortran-based model that has the cap. It's already it can basically produce hurricane based on Holland B and some of the variation of Holland B model. It basically generates the hurricane forcing, and it can basically support any other models in NOAPC application by providing surface wind and surface pressure. We also developed a couple of data caps to wrap different model output. At the moment, we have a data cap for unstructured atmospheric model. We have a data cap for a structured model, specifically for HFIP output. So we generate NetCDF file from HFIP, and then we can use the cap to wrap that output. We are also working on generating a cap for global RTOFs to kind of include baroclinicity in our coastal ocean modeling and storm surge modeling. I can tell you a little bit more about that one. This is really the activity we just about to start. WaveWatch 3 cap was developed and maintained by EMC team, and we are already tested AS1, and it's worked both for structured and for unstructured. So this is really the model we are kind of pulling in as a model component for Wave. And the ice model has a cap, and we are now just got that one in a collaboration with Grail. We just got that one tested for like a toy problem, but this model component also soon will be part of coastal application. We are also working very closely with developers of National Water Model at National Water Center, and this is also being going on. The cap is in development by the team at National Water Center, and we are working closely to bring that one also into coastal application. The next topic I want to talk to you about it is our global surge and tide operational forecast system. I list here also a couple of publications related to that this topic. So the STOF's Global version 2 just got updated around a month ago. The model engine for this system is ATSERC. So we used to have three different model domains for Micronesia, Pacific, and for Atlantic. So in November 2020, we merged all of this into a global system. And we also included a couple of high-resolution insets for specifically for U.S. waters, for Hawaii, for Pacific Island, and other parts of U.S. waters. And so for U.S. water areas, the nominal resolution is around 100 meter, from 80 to 220 meter. In the update that we made in just more or less a month ago, so we also included high-resolution inset for Puerto Rico area. So we also had the now we have high resolution all the way to 120 meter resolution and 10 meter above mean sea level for Puerto Rico area implemented. In the latest upgrade, as I said, we also included levees in lower Mississippi area. So here is just 1 year result for 1 year hindcast validation result. That shows that we have a good agreement with observations starting from Battery in New York here, top left, and then basically middle left is at North Carolina. You see also signature of Hurricane Dorian, and bottom left you can see the signature of Barry in lower Mississippi area, and top right is Santa Barbara in California, and then a station in Alaska. So we are happy with the with the results and with the skills of the global model so far. Just to give you an idea about also how details are the implementation for this 120-meter resolution, as well as to give you an idea about the federal levies that got implemented in the recent upgrade in Louisiana and right-hand side, the yellow lines. So moving forward, so how to access STOF's global results? So we are maintaining this site at the moment. It's thanks to EMC collaborator. We are hosting this site at the moment at NCEP, and you can kind of look into the skills of the models for the latest kind of solution. You can look into also a variety of different statistics like RMSE or peak error and others, as well as comparison, water surface elevation, time series, and some skills for specific stations. We are also collaborating and basically partnering with SARA system. Meanwhile, we are working on a Nowcast to kind of host this data, and we already can show some of the results from the in Nowcast system. However, with SARA, you can really zoom in to the result on a native mesh and look at the result in more details. Here, for instance, we are looking at Hurricane Ida at August 29. And if I zoom in here in a New Orleans area, and you also have this possibility to click in at any model area and get the water surface elevation. And even if you want to download the time series for that given area, you can kind of use this download button here and then get the kind of JSON time series of the model at that location. As I said, we are working on a Nowcast system to implement similar functionality in Nowcast, but at the meantime, we are relying on SARA for some of the functionality they can provide. If you want to try the system, the default is not on this system, so you need to use this user ID, nos.search at NOAA.gov as a user ID, and nos.search as a password. And then you will get a drop-down menu top right, and then you can choose STOFs, and then you can look into the global STOFs global results. Moving on. So as I mentioned in our R2O part, we are also working on to develop inland coastal compound flooding guidance system as a kind of component to a current STOF's operational system that we are running on NCEP. So these are a couple of publications that we used. So we also far developed this system and had couple of compound flooding storms like Hurricane Harvey and Hurricane Florence and Irene fully tested and implemented. However, we are still working on finalizing the mesh for Atlantic, and we have the system on pre-operational testing. So this is, to the best of our knowledge, is the world's first basin scale flexible inland coastal flood modeling system. It can go fairly high resolution all the way to 20 meter, 25 meter, and for resolving the levees, we even went all the way to maybe 1 meter, 4 meter resolution. And as you can see, still the model is not really bound by time steps. So the time step is still, can you keep it on 150 seconds? And if they are interested, and we can dive in deeper and maybe even given a specific seminar on this system that is almost being finalized. So in terms of the inland, in terms of the horizontal mesh and implementation of national water model, as you can see here, I like to draw your attention to top right figure here. So it's in Mississippi area, lower Mississippi area, and the red line is the boundary of the schism model. And we also overlaid on top of that all the branches and feature IDs of National Water Model. So basically, you can see how National Water Model features and rivers and streams are getting basically intersected with the boundary of the mesh, the red line. So, and on the bottom top right bottom one, you have a zoom in to see how again the red line and the feature IDs are getting a kind of the National Water Model streams are getting intersected. And normally what we do is we find the closest node, closest cell, and inject the discharge of that specific stream right there. And on the right hand and left hand side, you can see that how we are using the same network to guide the mesh generation, and basically have higher resolution where we have those networks to be able to resolve those networks. Moving to the next one, I just want to give you an idea about the domain. Top right is the domain. Now we are moving to left and zooming into lower Mississippi area. You can see how we are resolving this domain. And again, bottom left, more zoom in lower Mississippi area and New Orleans area. And then at the end, I like to draw your attention to the bottom right, where bottom right is the most kind of zooming completely around the Mississippi River. And if you can see that we can also morph from rectangular mesh to triangular mesh and back to rectangular mesh. And those meshes very close together, right beside the river, are the levees. So we are explicitly resolving the levees in this modeling system. And we show that also the overtopping is being resolved, and it's not going to be analytical solution. It's really the model is capable of performing the overtopping as well. In terms of the vertical mesh, so the model is capable of merging the vertical layers starting from the ocean. As you can see, for instance, in any of the bottom figures, in the ocean side, we can have almost like 45 layers. As we go toward the coast, following this transect, let's say in Delaware area, the red dashed line, as we go towards the coastline and in basically shallow water, we can start merge the layers. And in a river area, we only have one layer. So basically, if you remember from the previous slide, in coastal area, we have very high resolution, but low resolution in deep ocean. On the other hand, in deep ocean, we have fairly high resolution vertically, but then low resolution vertically in a shallow water area. So the model is also kind of load balanced automatically out of the box. And the other capability is that this model is highly stable. It's basically very difficult to break this model, and doesn't have any sensitivity to bottom roughness, so no smoothing at all to the bottom topography and bathymetry. So these are the capabilities that makes us very interested to this model almost like maybe more than 4 years ago when we start this partnership. Again, this is just another figure to show how the merging of the vertical mesh kind of looks like. So I'm going to only show you one kind of slide on the implementation, kind of the hindcast and test for Hurricane Harvey. So left-hand side, you see Hurricane Harvey region and impacted area. On the right-hand side, you see like a different runs. So the red dash line is the observation, and we saw here the different baseline. The green baseline is the one forced only by National Water Model input. And the black one is basically the one that what we are thinking of it as the best result, and the blue dashed line is the one that forced with USGS data. And we find out that not all of the National Water Model discharges are accurate. So for this specific hindcast, we kind of took majority of the inputs from National Water Model. However, where we had USGS observation for discharges available, we switched to the discharge from USGS. And as you can see here, the black line shows more improvement and more kind of according to the observation here. So that's the hindcast. But for the forecast, we are 100% relying on National Water Model discharges. So again here, this is from our pre-operational testing that I mentioned. For Hurricane Ida, I pulled this information from Hurricane Ida. So the model right now does 1 day nowcast and 2 day forecast. And the reason is that we are using HAR as a second level or high resolution atmospheric forcing. So basically the model is being forced by GFS, but in a coastal area, we substitute the wind from HAR and use HAR product for atmospheric forcing. At the moment, we are performing 4 times a day 2D model test and 3 times a day, one times a day 3-dimensional testing. And for Atlantic, and as I mentioned here, atmospheric forcing is GFS plus HAR. And for inland hydrology, we are relying on National Water Model. And again, just to make it again clear, we are including all of the National Water Model features that are intersecting with the boundary of the mesh. And inside the mesh, we are using precipitation to generate the runoff inside the modeling domain. So we are only using discharge of the National Water Model as an input and injecting the discharges to our modeling domain. So bottom left, you can see the domain and Hurricane Ida path on it. Zooming in on the top, you see the impacted area. This is also at August 29 kind of run. And in the right-hand side, I have a zoom in on New Orleans area. And as you can see, model predicted the overtopping, and you can see that we have quite a large area of the city inundated. I didn't really have a time, and I don't have resources to see how accurate is the model, but just looking at one of the stations, this is again only model result. You can see that water surface elevation time series also show some type of a 2 peak here. The second peak might be related to the storm itself or related to inland flooding or river flooding, which we are not sure yet. We need to spend more time and investigate this more clear and more closely. I have actually an HTML file. I can show you how we can zoom into different area of this model result later in Q&A if we have time. So we're also working and partnering with other part of NOAA on Coastal Ag project. We are supporting the storm stage modeling component. I'm not going to talk about this specific project in more detail. We have basically that NSEM name a storm event model that mainly comprise of 3 main components: surge model, wave model, and hydrology model, and of course being forced by atmospheric forcing in a one-way manner at the moment. And these 3 modeling systems supposed to be fully coupled and exchange information kind of dynamically. Here is in the top, in the right-hand side, I just showed you the coupling architecture at the moment. As I said, coastal ocean model or storm surge model is being supported by our team at National Ocean Services, but a wave model, atmosphere, and inland hydrology also is being supported by National Weather Service, EMC, and National Water Center. So just to show you an animation, this is an animation for Hurricane Sandy. So let me just pause it for a moment, give you an idea of where we are looking, what we are looking at. Top right is wind speed based on HFIP only result. Top left is wave height from wave watch 3. Bottom left is the surge, dynamic surge, basically from based on ATSIRC result, and in the bottom right you see the maximum surge during the whole period of the simulation. So as you can see, wind. It's just a zoom in the landfall area. So we have wind all the way to more than 30 meters per second, generated waves almost to 13-15 meters. So the maximum value is here, like around 13 meter wave height. And then the surge is, this is again also surge, which is total water level minus tide. So we are looking at more than 4-meter surge in the area. And this is the one that we are kind of doing for Coastal Act. One of the last part I want to talk to you today is about our effort for hurricane surge on demand. As I said, this system is not in operation at the moment. However, we are spending good amount of time and resources to kind of make it more agile and less computational demanding, and also adding more features to it. So hopefully in the future, we can see this system in operation again. So specifically, again, this is a kind of the architecture, coupling architecture we are working on in close collaboration and partnership with EMC at National Weather Service. So again, coastal ocean model, at the moment we are implementing ATSIRC, wave watch 3, and as I said, we also implementing this Fortran code for tropical cyclone which have actually already capable of coupling to NUOPC application and providing surface wind and surface pressure to both coastal ocean model ATSIRC and wave watch 3 wave model. And as I said, we also started to work on global RTOFs CAP to wrap the output of global RTOFs to calculate baroclinic effect and also force our 2D ATSIRC model with baroclinic effect. So that was the coupling part. We are also working on improving the system by ensemble storm surge. So 2 things is going on for ensemble part. One, we are trying to reduce the computation by using more, let's say, effective meshes. So we don't need to have full resolution all around the Atlantic. We may be able to subset the mesh only in impacted area, or even generate the mesh on the fly based on the predicted track. So that's one line of work at the moment. The other one is just looking to optimal ensemble generation. So we already implemented some Python packages, and again, those are all already open source on OCS GitHub, as I showed you for coastal application. We are mainly looking into, at the moment, the methodology is very much similar to P-Search, and we are looking to P-Search, how the error bounds is working, and we are trying to figure out how we can basically use that system as our guide for implementation. However, we decided to go with Python in terms of language of implementation at the moment. So that's basically it. I want to wrap up more or less in 2 or 3 minutes here. This is just kind of our implementation for on-demand unstructured mesh generation. So as we can see here, for instance, this is for Hurricane Florence, and this is done basically on Python, and the package is developed in Python. The background mesh generation is Jigsaw, is a C++ fairly fast package, but the management and putting together the data is done by Python, and our team is developing that. So here is an example for Hurricane Florence. The red are the wind SWOT that we are using as one guide, one of the guides for deciding where are the impacted area. And we have other criteria and working on the other criteria to detail how we can determine the impacted area. And then when we determine the impacted area, then we are going to use that impacted area to have a high resolution mesh. For instance, here we are using 200 meter. And also we are kind of also extending that area to 10 meter above mean sea level. However, for the rest of the area, we reduce the resolution to 1,000 meter and away from that with 20 kilometer to reduce the computation. So using this method, and also we are working on subsetting, we will be able to reduce the mesh size to 1/3 based on the type of the storm. So this is really an ongoing research, and again, if anybody is interested, we are willing to talk more and learn more from you as well. Again, we also are pretty active on community engagement, holding workshops. We were at AMS and AGU, and we are going to be at AMS 2022 and also Ocean Science 2022. We have this session, Coastal Ocean Modeling in support of marine navigation and blue economy, and as a part of it, it also has disaster mitigation. And I don't want to spend more time on this, so we are also spending time on organizing meetings and workshops, and also letting know how you can use basically the result of the models. So I guess I already mentioned quite a bit about everything here. I just want to release the time more for questions. We are at a 2:45 mark. And yeah, so I guess at this point I can release the screen and maybe switch to Q&A.
Thank you, Saeed. Jenny, you could start.